In 1939, General Motors built a diesel locomotive so cheap that railroad executives laughed at it. 85 years later, some are still running 24 hours a day. What did a $15,000 switcher know that million-dollar modern locomotives forgot? November 12, 1939, LaGrange, Illinois. The engineering specifications being reviewed by Santa Fe Railway's chief mechanical officer would determine whether American railroads embraced or rejected the diesel revolution. A 600-horsepower switcher locomotive that cost less than a used steam engine couldn't possibly deliver the reliability that railroad operations demanded. Through the morning frost covering Electromotive Division's testing yard, the SW1 switcher sat with an appearance that matched its bargain basement price. No streamlined body, no artistic flourishes, no engineering prestige that characterized the glamorous passenger diesels already capturing headlines. Just a boxcar-shaped hull containing an engine that General Motors promised would revolutionize yard operations while costing 60% less than comparable steam switchers. If you want to see more videos about old trains that outlasted everything modern, make sure to subscribe so you never miss another video. Traditional railroad mechanical departments had spent decades perfecting steam locomotive maintenance. Every railroad employed crews who understood steam engine overhauls, carried parts inventories for established designs, and operated roundhouses equipped for steam locomotive servicing. The institutional knowledge represented billions of dollars in invested expertise and infrastructure that diesel locomotives threatened to make obsolete overnight. The numbers told a story that seemed mathematically impossible. An SW1 diesel cost $15,000 new compared to $25,000 for equivalent steam switchers. General Motors claimed operating costs would run 40% lower than steam with maintenance intervals 3 times longer. But no American railroad had operated diesel switchers long enough to verify whether these promises represented engineering reality or sales department optimism. Santa Fe's mechanical officer faced a decision that would influence locomotive purchasing across the entire American railroad industry. The railroad operated hundreds of switching locomotives in classification yards where freight cars were sorted, assembled into trains, and dispatched to destinations. Each switcher worked 12 to 20 hours daily under conditions that destroyed equipment lacking fundamental durability. Steam switchers required constant attention from maintenance crews who understood that boilers, fireboxes, and running gear demanded skilled care to prevent catastrophic failures. Water treatment, ash disposal, coal handling, and daily inspections consumed hours that reduced productive switching time. The promise of diesel operation meant eliminating these maintenance requirements, but only if EMD's engine could withstand punishment that had broken previous diesel attempts. The diesel locomotive concept wasn't new. Several manufacturers had introduced diesel switchers during the 1920s, creating expensive machines that required more maintenance than the steam engines they were supposed to replace. Electrical failures, engine breakdowns, and transmission problems had convinced most railroads that diesel technology remained fundamentally unreliable for heavy industrial service. But the Electromotive Division claimed to have solved the problems that defeated earlier diesel builders. Their 2-cycle diesel engine eliminated complex valve mechanisms that caused maintenance headaches. Electrical components were standardized across their entire product line, ensuring replacement parts availability. Could a $15,000 locomotive truly deliver reliability that expensive steam switchers couldn't match? By 1938, American railroads faced an operational crisis that threatened their economic survival. Classification yards scattered across the nation consumed enormous resources moving freight cars between trains, but the steam switchers performing this work operated at efficiency levels that would bankrupt the industry within a generation. The mathematics of steam switching operations revealed costs that couldn't be reduced through operational improvements alone. Each steam switcher required a 3-man crew: engineer, fireman, and hostler. Labor costs for operating a single switcher 24 hours daily exceeded $12,000 annually. Add fuel, water, maintenance, and facilities costs, and total annual expenses reached $20,000 per locomotive. Maintenance demands created bottlenecks that reduced switcher availability below acceptable levels. Steam locomotives required daily servicing that included ash removal, firebox cleaning, boiler water treatment, and lubrication of dozens of moving parts. Major overhauls occurred every 18 months, removing switchers from service for weeks while skilled craftsmen rebuilt worn components. The hostler's role exemplified the complexity of steam operations. This specialized worker maintained fires overnight, ensured adequate steam pressure for morning operations, and performed the constant monitoring that prevented boiler failures. Hostlers represented an entire employment category that diesel operations could eliminate, but only if diesel engines proved reliable enough to start instantly without hours of preparation. Railroad mechanical departments operated massive infrastructure supporting steam locomotive fleets. Coaling towers, water treatment plants, ash pits, and roundhouses represented capital investments exceeding $50 million for major railroads. Converting to diesel meant writing off these facilities while simultaneously investing in new maintenance infrastructure before anyone knew whether diesel technology could deliver promised reliability. The Great Depression intensified financial pressures that made locomotive purchasing decisions critically important. Railroads operating on thin profit margins couldn't afford expensive mistakes in equipment selection. If diesel switchers failed to deliver promised savings, the railroads would face both the cost of failed diesel experiments and the continuing expense of steam operations they couldn't afford to maintain. Competition from trucking companies eroded railroad freight revenues throughout the 1930s. Highway systems improved by federal spending allowed trucks to capture short-haul freight that had previously moved exclusively by rail. Railroads needed operating cost reductions to compete with truck shipping rates that undercut rail prices through lower labor costs and minimal infrastructure requirements. The switching problem affected every aspect of railroad operations. Freight cars spent days in classification yards waiting for switchers to assemble trains. Delayed car movements reduced railroad capacity, forcing companies to own larger freight car fleets than efficient operations would require. Every hour saved in yard switching translated directly to improved asset utilization and reduced capital requirements. Terminal managers calculated that diesel switchers working continuously could replace steam switchers that spent hours each day in servicing facilities. But continuous operation demanded reliability that no diesel manufacturer had demonstrated conclusively. Would the SW1 prove different from previous diesel failures, or would it join the expensive mistakes littering railroad scrapyards? Charles Kettering's engineering philosophy at General Motors revolutionized diesel locomotive design through a principle that contradicted everything established. Engine builders believed necessary for reliability. Make it simpler, not more sophisticated. The EMD 567 diesel engine powering the SW1 switcher eliminated components rather than adding them. Traditional diesel engines used four-stroke cycles, requiring complex valve trains, camshafts, and timing mechanisms that created hundreds of failure points. Kettering's two-stroke design eliminated intake and exhaust valves entirely, using piston movement to control airflow through strategically positioned ports in the cylinder walls. Fewer moving parts meant fewer components that could break, wear out, or require adjustment. The engine displaced 567 cubic inches per cylinder, a measurement that became the model designation and revealed EMD's manufacturing philosophy. Standardized displacement across every cylinder meant identical pistons, rings, and liners throughout the engine. Maintenance crews could stock one set of parts rather than managing inventory for dozens of different specifications. Cylinder construction used wet liners that could be replaced individually without removing the entire engine block. When a cylinder wore beyond acceptable limits, mechanics unbolt the cylinder head, lift out the worn liner, and install a replacement in hours rather than the days required for complete engine rebuilds. This modular approach transformed major overhauls into routine maintenance procedures requiring minimal downtime. The Roots blower forced air into cylinders through a scavenging process that cleared exhaust gases while filling cylinders with fresh air for the next combustion cycle. This positive pressure system eliminated the complex exhaust valve mechanisms that plagued four-stroke diesels. The blower itself contained only 3 moving parts, 2 rotors and a drive gear, creating a supercharging effect without the reliability problems of turbochargers or mechanical compressors. Electromotive Division's electrical system standardized components across their entire locomotive product line from switchers to passenger units. The same generator model, control contactors, and traction motors appeared in multiple locomotive types, ensuring parts availability and reducing training requirements for maintenance personnel. Electricians familiar with passenger diesel maintenance could service switchers without learning completely new systems. Fuel injection used unit injectors that combined pump and spray nozzle in single components mounted directly in each cylinder head. Previous diesel designs used complex injection pumps feeding multiple cylinders through high-pressure fuel lines that leaked, cracked, or required constant adjustment. Unit injectors eliminated external fuel lines while providing precise fuel metering that optimized combustion efficiency. The cooling system circulated water through passages designed for maximum heat transfer with minimum flow restriction. Oversized radiators provided cooling capacity exceeding normal operating requirements, ensuring the engine maintained proper temperature even during extended periods of maximum power output. This thermal margin prevented overheating damage that destroyed engines designed with minimal safety factors. But the most revolutionary aspect wasn't engineering, it was a business model. EMD didn't just sell locomotives. They sold standardized parts, trained railroad mechanics, and guaranteed parts availability within 24 hours anywhere in North America. Professional engineering societies responded to EMD's claims with skepticism rooted in decades of diesel. Locomotive failures. The American Society of Mechanical Engineers published analyses questioning whether simplified two-stroke engines could withstand continuous duty cycles that railroad switching demanded. Dr. Heinrich Nordmann, chief mechanical engineer for Pennsylvania Railroad, represented the conservative approach dominating railroad mechanical departments. His technical papers documented diesel failures that had cost American railroads millions in scrapped equipment. Automotive-derived engines lacked the robustness necessary for locomotive service, he wrote in Railway Age magazine. General Motors builds cars, not industrial power plants. The technical criticism focused on lubrication systems that Nordmann considered fundamentally inadequate for continuous operation. Four-stroke diesel engines used pressure lubrication systems delivering oil to every bearing surface through dedicated pumps and filtration equipment. EMD's two-stroke design mixed lubricating oil with fuel, relying on combustion byproducts to provide cylinder wall lubrication through methods that seemed primitive compared to established practice. Union Pacific Railroad's mechanical department calculated that two-stroke engines would consume lubricating oil at rates making operational costs higher than EMD's projections suggested. Their analysis predicted oil consumption exceeding 1 gallon per 100 miles compared to negligible consumption in four-stroke designs. Over a switcher's annual mileage, this difference would eliminate claimed cost advantages while creating disposal problems for waste oil volumes no railroad was equipped to handle. Santa Fe Railway accepted delivery of their first SW1 switcher in January 1940 with testing protocols designed to reveal whether EMD's promises matched operational reality. The locomotive entered service at Barstow, California, one of the railroad's busiest classification yards, where 24-hour operations provided ideal conditions for accelerated durability testing. Mechanical inspectors monitored the switcher daily, recording oil consumption, engine temperatures, electrical performance, and maintenance requirements that would determine whether additional diesels replaced the railroad's steam switcher fleet. The testing deliberately subjected the locomotive to punishment that would reveal weaknesses quickly rather than discovering problems after purchasing multiple units. The SW1 worked continuously for 90 days without mechanical problems beyond routine inspections and lubrication. Oil consumption measured 0.7 gallons per 100 miles, 30% below Union Pacific's predictions and well within acceptable operational parameters. Engine temperatures remained stable even during extended periods of maximum power output in desert heat exceeding 110 degrees Fahrenheit. More significantly, the switcher required no repairs during the test period, while steam switchers operating alongside needed constant attention from maintenance crews. The diesel worked 20 hours daily compared to 12-hour average availability for steam units requiring servicing breaks. This operational advantage translated to productivity improvements that exceeded EMD's conservative estimates. Railroad mechanical journals began publishing field reports from early diesel adopters, whose experience contradicted the skepticism that dominated professional engineering opinion. But 90 days couldn't prove long-term durability. Would the SW1 maintain this performance after 5 years of continuous service, or would it join previous diesel experiments in the scrapyard? December 1941, transformed railroad operations overnight as military traffic overwhelmed existing locomotive capacity. Classification yards that had handled 200 cars daily suddenly processed 800, creating switching demands that pushed every locomotive beyond design limits. EMD's production expanded from building 20 locomotives monthly to over 100 as railroads desperate for motive power ordered anything available. But the SW1 switchers, already in service, faced the ultimate durability test: continuous operation under conditions that destroyed equipment designed for peacetime schedules. Baltimore and Ohio Railroads, Cumberland, Maryland. Yard operated 37 SW1 switchers throughout the war years, maintaining detailed maintenance records that documented performance under stress no peacetime operation could replicate. These locomotives worked 23 hours daily, with 1 hour reserved for fueling and routine inspections. The duty cycle exceeded anything EMD's engineers had considered during design phases. Monthly reports revealed operational statistics that contradicted every prediction about diesel locomotive durability. After 18 months of wartime service, the SW1 fleet averaged 4,300 hours between failures requiring shop work. Steam switchers operating alongside averaged 800 hours between shopping, requiring constant mechanical attention that diverted skilled workers from war production factories. Component wear patterns demonstrated the value of EMD's design philosophy. Cylinder liners showed minimal wear despite extended operation at maximum power output. The wet liner design allowed individual cylinder replacement during scheduled maintenance without removing engines from locomotive frames. Mechanics could complete cylinder replacement in 8 hours compared to the 3-week engine rebuilds required for conventional diesel designs. The Roots blower exceeded all durability expectations despite operating continuously at speeds that should have caused rapid wear. 1944 inspections of blowers with 10,000 operating hours revealed clearances within original manufacturing specifications. The simple 3-component design proved more durable than complex turbocharging systems used by competing diesel manufacturers. Electrical system reliability validated EMD's standardization strategy. Generator failures occurred so infrequently that railroads reduced spare parts inventory levels below requirements for steam. Locomotive electrical components. Traction motors operated throughout the war without rewinding or bearing replacement, demonstrating that automotive-derived electrical equipment could withstand industrial service when properly designed. Fuel consumption data collected across multiple railroads established operating cost advantages that exceeded EMD's conservative estimates. SW1 switchers consume 0.4 gallons of diesel fuel per switcher hour compared to 0.8 tons of coal for steam switchers performing equivalent work. At wartime fuel prices, this translated to operating cost savings of $12 per locomotive per day. The Pennsylvania Railroad's Mechanical Department, previously skeptical of diesel reliability, published internal reports recommending complete conversion to diesel switchers based on wartime performance data. Dr. Nordman acknowledged that EMD had achieved what established diesel manufacturers could not: industrial-grade reliability from simplified design philosophy. By 1945, over 1,000 SW1 switchers operated across North American railroads. The war had proven that cheap didn't mean disposable. The post-war era brought the real revelation about SW1 durability. As railroads returned to peacetime operations, the wartime switchers that should have been worn out continued working without the major overhauls that steam locomotives required every 2 years. Southern Pacific Railroad's Oakland Yard maintained operational records tracking locomotive reliability from 1946 through 1965. Their 11 SW1 switchers accumulated an average of 98,000 hours each during this period, with total maintenance costs averaging $400 annually per unit. This included all repairs, routine servicing, and parts replacement. The comparison to steam switcher lifetime costs revealed the magnitude of EMD's achievement. Steam switchers required complete boiler replacement after 20 years of service at costs exceeding $10,000 per locomotive. SW1 diesels approaching 25 years of service needed cylinder liner replacement costing $800 and generator rewinding at $2,000. No other major components required replacement. Union Pacific discovered that SW1 locomotives built in 1941 remained structurally sound in 1966, prompting engineering studies examining why the switchers outlasted their design service life by decades. Metallurgical analysis of frame components revealed minimal fatigue damage despite millions of stress cycles from starting, stopping, and constant vibration. The engine blocks showed the wisdom of conservative design margins. EMD rated the 567 engine at 600 horsepower, but dynamometer testing revealed the engine could produce 800 horsepower continuously without exceeding design stress limits. This power margin meant the engine operated at 75% of maximum capacity during normal service, extending component life far beyond typical industrial diesel applications. Rock Island Railroad experimented with SW1, rebuilding programs during the 1970s, replacing worn components while retaining original engine blocks and frames. The rebuilt locomotives cost $4,000 compared to $90,000 for new switchers, yet delivered reliability matching new equipment. This established SW1 rebuilding as standard practice across the industry. By 1980, railroads operated SW1 switchers built 40 years earlier alongside modern locomotives costing 20 times more. Maintenance supervisors discovered that older SW1 units frequently proved more reliable than new switchers using advanced technology that increased complexity without improving fundamental durability. Norfolk Southern Railway conducted comprehensive reliability studies in 1988 comparing SW1 switchers built in 1939 with modern switchers manufactured in 1985. The 49-year-old locomotives showed lower failure rates than 7-year-old units, despite operating in identical service. The industrial diesel engine market adopted EMD's design philosophy after observing railroad experience. Stationary power plants, marine propulsion systems, and pipeline pumping stations specified 567-based engines for applications requiring multi-decade service life. But the original SW1 switchers continued outlasting industrial engines built using the same basic design. Some railroads discovered SW1 units approaching 50 years of continuous service without frame replacement or major structural repairs. The cheap gamble had become the most durable locomotive ever built in North America. 21st century locomotive manufacturing abandoned the principles that made the SW1 indestructible. Modern switchers entering service in 2005 began experiencing catastrophic failures within 5 years, creating maintenance costs that exceeded the SW1's entire lifetime expenses. General Electric's Model Evolution Series locomotives cost $8 million each, featuring computerized engine management, emissions controls, and advanced electrical systems designed for regulatory compliance rather than longevity. Railroad mechanical departments discovered these sophisticated machines required specialized diagnostic equipment, manufacturer-trained technicians, and proprietary replacement parts unavailable through competitive suppliers. The complexity multiplication paralleled the shift from Carnegie's integrated steel production to modern outsourced manufacturing. Modern locomotive builders assembled components from global supply chains with no single entity controlling quality throughout the production process. Engine blocks from one supplier, fuel injection from another, electrical components from third contractors created integration problems that generated failure modes impossible in the SW1 standardized design. Canadian Pacific Railway's mechanical department documented the cost differential in 2000. 18 annual reports. Their surviving SW1 switchers built in 1942 showed annual maintenance costs of $1,200 per unit. Modern switchers manufactured in 2012 averaged $12,000 annually, with major component failures requiring $40,000 repairs before reaching 10 years of service. The emission control systems mandated by environmental regulations created the most severe reliability problems. Diesel particulate filters, selective catalytic reduction systems, and exhaust gas recirculation components failed frequently, removing locomotives from service for repairs that SW1 switchers never required. The environmental equipment alone cost more than the entire purchase price of an original SW1. Electronic engine controls replaced mechanical fuel injection with computer-managed systems that optimized emissions and fuel economy. But software glitches, Sensor failures and electronic component degradation created maintenance requirements that mechanical systems had avoided entirely. Railroad mechanical departments needed electronics specialists rather than diesel mechanics, transforming maintenance from mechanical troubleshooting to computer diagnostics requiring manufacturer support. BNSF Railway continued operating SW1 switchers built in 1939 at their Argentine yard in Kansas City through 2022. These 83-year-old locomotives worked alongside modern switchers costing 120 times more while requiring a fraction of the maintenance attention. When the railroad finally retired the last SW1 from regular service, the locomotive went to a museum rather than a scrapyard, still mechanically functional after 8 decades. The engineering lesson remains visible in every rail yard where ancient SW1 switchers outlast modern locomotives designed by computers, tested in laboratories, and built with technology the 1939 engineers never imagined. Why did a $15,000 diesel built with 1930s technology outlast $1 million modern locomotives that can't survive their warranty periods?